about changes in the states of matter. Now you know there are three states of matter. There are solids, there are liquids, and there are gases. And you probably know that when a solid like ice turns into a liquid, we say that it's melting. And if a liquid like water turns back into a solid, we can say that it's freezing. But it turns out they're names for all of the other types of changes that can exist as well. If a liquid turns into a gas, like when you boil a pot of water, we say that the liquid is evaporating. This is an example of evaporation. There are also times when a gas will turn back into a liquid. If you've ever had a bottle of cold water, you see these little droplets of water form on the outside. This is happening because water vapor, or gas in the air, is turning back into a liquid because of the cold water inside of the bottle. We call this process when a gas turns back into a liquid condensation. There's one more example too. Believe it or not, but a solid can turn directly into a gas without ever having to be a liquid. This happens with dry ice, which is solid carbon dioxide. If you drop it in some water just to start the reaction, you can see that the carbon dioxide ice is turning directly into a gas. It's never becoming a liquid. Those solid chunks are switching directly into a gas. Now this process where a solid goes straight to a gas is called sublimation.
When the gas changes to solid, we call as deposition. A phase is a physically separate part of the system with distinct physical and chemical properties. It is the homogeneous region separated by a distinguishable boundary. Referred to the figure shown here, we can see that the system consists of solid, which is ice, liquid, which is water, and gas, which is water vapor. Phase diagram is a graphical representation of chemical equilibrium. Since chemical equilibrium is dependent on the composition of the system, the pressure and the temperature, a phase diagram should be able to tell us what phase is most stable at any temperature and pressure of the system. The phase diagram allows us to predict element phase based on the temperature and pressure of the environment. Each line represents the set of temperature and pressure at which the two phases on both sides of the line coexist in equilibrium. General shape for a phase diagram. On the x-axis, we have temperature. On the y-axis, we have pressure. Lines shown to us represent the boundary between two phases. Two phases can exist together at equilibrium. P, Q, and R represent the area or region, which is a condition under which the substance will be in that particular phase. Now we look at each line. Line A, O, B. Line AO is solid gas at equilibrium. Process changes is sublimation or deposition. Line OB, solid liquid at equilibrium. Process changes is melting or freezing. It represents to us solid area. Now line B, O, and C. Again, line OB is solid liquid at equilibrium. Process changes is melting or freezing. Line OC, liquid gas at equilibrium. Process changes, condensation or evaporation. It represents to us liquid area. Line A, O, C. Again, line AO, solid gas at equilibrium. Process changes is sublimation or deposition. Line OC, liquid gas at equilibrium. process changes is condensation or evaporation. It represents to us gas area. In the phase diagram, there exist two interesting points, which is a triple point and critical point. Triple point, where the three phases of solid, liquid, and gas can exist together at equilibrium. This is where the three lines meet together. And the critical point gives the highest temperature at which the substance can exist in the liquid phase. If the liquid-gas line ends above this point, the liquid and a gas phases become indistinguishable.